Introduction and Chemistry 20 review. This is Lewis dot structure, something new for you. Goes along with assignments BR15 to BR17. Lewis dot is used to determine the shape and bonding arrangements for covalently bonded molecules. These can be used to explain and even predict things like how well they will dissolve in certain liquids, melting and boiling points, and other physical properties of the molecule. Plus, hey, I think it's a lot of fun. Lewis dot was my favorite thing to do in chemistry when I was a student. So how many dots does each element get? Well, that depends on the column that element is found in. In the first column, all the elements, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, they all are given 1 dot. The second column, they are all given 2 dots. Now we skip over that middle section. That's called the D block, and it is way too complicated for us to deal with in first year, second year chemistry, and definitely high school. So we skip that. We jump over to boron, and everyone in boron's column will be given 3 dots. Carbon's column gets 4, nitrogen 5, oxygen 6, fluorine 7, and everyone in the final column gets 8 dots, with the exception of helium, because helium is a noble gas with 2 electrons, so helium has 2 dots. So make sure you add that to your periodic table. Write the numbers over top the columns, and make the note that helium has 2 dots. It is the only exception to the rule that we're going to be concerned about. Now in Lewis dot, the dots represent electrons. And when I'm adding Lewis dots, or if I'm adding electrons to the symbol, this is the order that we follow. The first electron can be added to any side of the atomic symbol. So we can either start on the top, bottom, left, or right. Only 1 electron is added to each side as we move either way around the atomic symbol. So you can add dots going in a clockwise fashion or a counterclockwise fashion. It really doesn't matter. And 3, once each side has a single electron, a second electron is added, continuing in that circular motion. So we're going to draw the Lewis dot structure for neon. Neon is in the column that has 8 dots. So I'm going to start by adding 1 dot to one side, either right, left, top, or bottom. Let's go top, and then I can go clockwise or counterclockwise. I'm going to go clockwise, so I add another dot. There, boop, boop, there we go. There's 4. I have 4 more I have to add, so I'm going to have to start doubling them up. So I put 2 on the top, 2 on the right, 2 on the bottom, 2 on the left. That's it, it's done. Now I want you to make a note that neon looks like this. It does not look like this. Now remembering that each dot represents an electron, dots are added if we have a negative charge, and dots will have to be taken away if there is a positive charge. Charge structures are put in square brackets, and the charge is written in the right-hand corner outside the brackets. So let's draw the Lewis dot structure for sulfide. Now, sulfur is in the column that has 6 dots. But since it has a -2 charge, I'm going to have to add on 2 more dots, which will mean sulfide has 8 dots. So I'll draw a big S. There's 1, 2, 3, 4, 5, 6. So that's what sulfur would look like if it wasn't charged. But again, I've got a -2 charge, so I have to add in 2 more dots. So there we go, 8 dots. Make some nice big square brackets, and then I write a -2 up in the right-hand corner. And that question is now complete. So let's say I'm drawing the Lewis dot structure for selenium, Se. There, Se is in the column that has 6 dots, so I'd write Se. I could start on the top, right, bottom, left, really doesn't matter. But let's say I started on the top and I went clockwise. That's what my answer would look like. Or if I started on the right-hand side and filled in my 6 dots, that's what I would wind up with. Or if I started on the bottom and then went clockwise, that's what my answer would look like. Or I could have started on the left-hand side, filled in my dots, and I would have wound up with this as an answer. All four are correct answers, just as long as the two lone dots are adjacent to one another and the two paired dots are adjacent to one another. Draw the Lewis dot structure for potassium. Well, potassium is in the column that has one dot, so I'd write a K and put a dot on the top, or I could have put that dot on the left-hand side, or I could have put it on the bottom, or I could have put it on the right-hand side. So any one of these would be an acceptable answer for the Lewis dot structure for potassium. And the last example in this set, draw the Lewis dot structure for chloride. So I've got Cl, which has 7 dots, and since there is a minus charge, I have to add a dot, so I will have to draw a Cl and place 8 dots around it. And since it had a negative charge, it will require square brackets with the negative charge written in the upper right-hand corner. We have heard on multiple occasions that elements want to have the same electron configuration as the noble gases. This is called the Octet Rule. Elements will gain, lose, or share electrons, so they have 8 valence electrons, just like the noble gases. Some atoms find sharing electrons with other atoms an easier way to fill their octet than losing or gaining electrons. This sharing of electrons is what creates bonds. Lewis dot diagrams are the best tool chemists have to predict the bonding arrangements of atoms in a molecule. Atoms want their electrons to hang out in pairs, so it is the unpaired electrons that will bond. So I want you to add these notes to your handout. Draw an arrow to these dots here. These electrons are already paired, they will not bond. Draw arrows to the other electrons. These electrons are single and the atom will want to pair them up. Again, add these notes to your handout. Atoms that bond with like elements are called diatomic elements. These are the Lewis dot diagrams for 4 of the 7 diatomic molecules that form. For hydrogen, I draw an H and give it 1 dot. Then I draw the second H and give it 1 dot. Notice I strategically drew the 2 lone dots facing each other because remember, it is the lone electrons that will bond. So these lone electrons will come together and form a bond, which we will draw as a stick drawn between the 2 hydrogens. The stick represents a bond, and inside that bond are 2 electrons. With fluorine, I draw an F and place 7 dots around the F. Then I will draw the second F, and again draw 7 dots around that F. Again, I strategically started and then drew my dots in such a way that I would wind up with the lone electrons facing each other so that they could bond. So drawing the molecule of fluorine, I will have F singly bonded to F, and I have to remember to draw those lone pair electrons around each of the fluorine. I will start by writing a giant N, and I need to put 5 dots around that N. So I'm going to start on the left-hand side so that when I have drawn all my dots, the lone electrons will be facing towards where I will draw the second N. And I will follow the same strategy, draw my dots around my nitrogen, all 5, so that the lone electrons are facing the other atom. Now the 2 electrons that are closest to one another will be able to bond. The lone electrons on the bottom will be able to bond, and the lone electrons on the top will be able to bond. And that will form what we call a triple bond between the 2 nitrogen atoms. For oxygen, I will start by drawing an O. I will draw in my 6 dots, Again, strategically placed so the lone electrons will face the other oxygen. And I will do the same thing with my second oxygen. Now the two electrons facing towards each other will be able to bond, and the two lone electrons on the bottom will be able to bond, meaning oxygen will double bond. Now note, when I drew oxygen, I spread the lone pairs out because electrons are negatively charged. They are all negatively charged, and since they all carry the same charge, and we know like charges repel, they will repel one another. So the electrons in the bonds and the electrons in the lone pairs are going to try to spread out as much as possible. Since I have a double bond, lone pair, that's three things. That means they will spread out 120 degrees from one another. That's as far as they can spatially get away from one another. So there are 120 degrees between the lone pairs, and there are also 120 degrees between the lone pairs and the double bond. As we move away from just drawing diatomics and start drawing more complex molecules, here's something to keep in mind. We start by drawing the central atom in the middle surrounded by the other atoms. The central atom is the one that can make the most bonds. And if there's a tie, well, the central atom is usually the least abundant element in the chemical formula. Now you may want to make a note on your pink sheet of the two following rules. Rule 1, the quadruple bond. Bam! Ain't gonna happen. You're not allowed to have more than 3 bonds between elements. Nowhere will you ever find a molecule that has a quadruple bond. So all we will draw in this class are single, double, or triple bonds in our molecules. Rule 2, a nice little circle of 4. Bam! Ain't gonna happen. Elements cannot bond in a circle with 4 or fewer members. At least they won't in this class. It is possible, but the molecules tend to be very unstable. So when we draw a circle, we will have a minimum of 5 atoms in that circle. Example 1, H2O. Hydrogen has 1 dot, so it can make 1 bond. Oxygen has 6 dots, so it can make 2 bonds. Since oxygen can make more bonds than hydrogen, I will write it down first. And then I will place the H's by oxygen's available electrons for bonding. So one on the bottom, one on the right-hand side. And the 2 lone electrons on the bottom will be able to form a bond, and the 2 lone electrons on the right-hand side will be able to form a bond. And when I draw it with the bonds in, this will be my final answer. Now, sometimes people say, why don't I spread the H's out? And that's because they can't. Everything is spread out as far as it can possibly get right now. I have 4 things around my oxygen. A lone pair, a single bond, and a single bond. That's 4 things, so that means they have to spread out as far as possible, which is 90 degrees between one another. Now, why don't I move the H to the opposite side of the other H? Remember when we said we add electrons clockwise or counterclockwise? That's because in the end, anything that's in oxygen's row, if it has 2 single bonds, they have to be adjacent to one another. We go clockwise or counterclockwise so that the lone electrons that will bond are adjacent to one another. So this is our final answer. I also want you to write this down and put a big "ain't gonna happen" on it. Example 2, Bi3. I have B, which is in the column that has 3 dots. So that means it has 3 lone electrons. It can form 3 bonds. Iodine is in the column that has 7 dots. That means it is left with only 1 lone electron, so it can only form 1 bond. So I will put B into my diagram first, and I will put an I in each one of boron's single electrons. That means that the I and B on the left can bond, the B can bond with the I on the bottom, and the B can bond with the I on the right. And that gives us this, but it can't be done because I have to make sure everything's spaced out. Boron is making 3 single bonds. And when there are 3 things around your atom, you have to make sure there's 120 degrees between each one of them because, again, they want to spread out. So I make sure there's 120 degrees between each one of those bonds. Now, if I look at each iodine, there are 4 things around them: a single bond, a lone pair, and another lone pair. So that means there has to be 90 degrees between each one of them. So bottom guy is easy. I got a bond on the top, so I'll put a lone pair on the right, bottom, and left-hand side, and that's done. Now the ones on the angle are a little more tricky to make sure that they are spaced out perfectly. And I hate to brag, but I was always complimented in university on how well I spaced out my electrons. Yes, and I will let you in on a little secret, probably going to pay huge dividends in the future when you do this. So I start by drawing the electrons on the opposite side of the bond. And then I put the ones that are on this side into my diagram second. Again, opposite side, put the dots on the opposite side of the bond, and then add in the 2 other lone pairs. And then that's it. Ooh, that's a thing of beauty. Example 3, CnH3. I have carbon, which is in the column that has 4 dots, so it is able to make 4 bonds. I have nitrogen, which is in the column that has 5 dots, so it is able to make 3 bonds. And I also have 3 hydrogens, each has 1 dot, so that means it's able to make 1 bond. I will start by placing the C on the piece of paper, and then I will go with the nitrogen because it is able to make the second most bonds. Now I have to add in my hydrogens. Now this is where we really get into the trial and error. So I'll try adding my 3 hydrogens around the carbons. And then the guys on the left can bond, on top, on the right, and the C and N can bond, but the N will not be happy because it is left with 2 electrons that have not been bonded. So we'll have to try something different. How about if we try those H's on the nitrogen? Well, that means the H on the left can bond, the H on the right can bond to the nitrogen, the carbon and nitrogen can bond together. Now the nitrogen is happy. That hydrogen will bond to the top, but I wind up with carbon now being unhappy because it has 2 electrons that have not bonded. So how about if we try moving one of the H's back over to the carbon? Well, then we can bond the hydrogen and carbon at the top, the one on the left to the carbon, and the hydrogen on the bottom can go to the nitrogen. And, well, carbon still has 2 lone electrons, and nitrogen still has 2 lone electrons. Why can't we form a double bond? Yes. And that's what that would then look like, right? And now that I've got everything bonded and everybody's happy, all their lone electrons have found a partner to hang out with, I have to now draw this with it properly spread out. Now the carbon has 3 things attached to it: a single bond, double bond. So there will have to be 120 degrees between each thing attached to the carbon. If I look at the nitrogen, it has a double bond, single bond, lone pair. That is also 3 things. So that means there's going to have to be 120 degrees between each one of those objects. So if I put the C on the top and the N on the bottom, I will make sure there's 120 degrees between the hydrogens that are added to the carbon, as well as 120 degrees between the double bond, single bond to the hydrogen, and the lone pair that's hanging out around the nitrogen. And that's it. Woo! That's a good time. And that's the end of the lesson as we know it.